Kepler's third law, also known as the law of harmonies, is a fundamental principle in astronomy that describes the motion of planets around the Sun. In simple terms, this law states that the square of a planet's orbital period, the time it takes to complete one full orbit around the Sun, is directly proportional to the cube of the average distance from the Sun. What that means is that the further a planet is from the Sun, the longer it takes for it to orbit the Sun. For example, Earth, which is closer to the Sun, orbits faster and takes 1 year to complete its orbit, while Mars, which is farther away, takes about 1.9 years. This relationship is consistent for all planets in our solar system. The formula for Kepler's third law is a cubed is equal to gm over 4 pi squared, which is all multiplied by t squared. In the formula, t represents the orbital period of a planet, which is the time taken to complete one full orbit around the Sun, measured in seconds. The variable a stands for the orbital radius, which is the average distance from the planet to the Sun, measured in kilometers. And the constant 4 pi squared over gm involves pi, which is the mathematical constant, g, which is the gravitational constant of 6.674 times 10 to the negative 11th power, and m, which is the mass of the Sun or any central body that a planet or moon is orbiting around. This constant ensures that the units and the scale of the solar system are accounted for in the calculation. Kepler's law indicates that the square of the period, t squared, is proportional to the cube of the radius, a cubed, showing that the further a planet is from the Sun, the slower it orbits and the longer its period. This relationship holds true across our solar system and helps astronomers calculate orbits and predict planetary positions. Using this formula, we will find the mass of Kepler 90 in accordance with Kepler's third law. However, the process itself is not so simple, as we cannot simply solve it with our current equation. We are trying to find the mass of the Sun, and yet the equation we have is finding the semi-major axis. So before we continue, we need to alter the equation so as to get m alone. Once we solve that, we will be free to solve the big question. To find the mass of that star, we need to find the linear fit of the graph from the semi-major axis cubed and orbital period squared. We will use the slope m to solve for the mass of the star. First, you will set up the equation big M times g over 4 pi squared is equal to little m, which is the slope of the linear fit, and then proceed to move g over 4 pi squared to the other side of dividing it. After you've gotten big M is equal to little m times 4 pi squared over g, you will plug in the numbers for g and m. In the end, you should get 2.46 times 10 to the 21st power in kilograms. That is how you use Kepler's third law to solve for a star's mass.